right now, the first approximation, humans are building AI. And what happens if AI starts building itself? And do we have an intelligence explosion? And maybe before we start talking about it, and I thought there was, I think, an interesting discussions on perusal on the pre-reading, and I thought like maybe we can have a little bit of discussions in class. So I just wanted to open it up like to thoughts anyone had while reading these documents or other documents. Anyone wants to start? Yes.
One thing that I think across all of the articles...
I don't know if everyone can hear, or maybe...
I can talk even louder if I need to.
Okay, I can even pass the mic, so...
One thing that I would have liked to see across all the articles, except for the one from Epic, is maybe a little bit more about the methodology. There were a lot of sort of N% chance of this, and sometimes that's just, forecasting is an expert science, which you can trust or not trust. Sometimes there's distributions, sometimes there's background knowledge, sometimes it's the product of a bunch of normal distributions, and I found it hard to figure out my own trust levels across these articles because there wasn't that methodology.
Yeah, and I think there is... One of the things I'm sometimes worried about with these, some of these forecasts is that we could have like an illusion of accuracy. When you have like a lot of numbers, then it seems very authoritative, where like ultimately it's very much like there's so many unknowns that like this level of accuracy, it's like, if I wanted to kind of, I gave you like the length of this whiteboard and I gave it to you with, in inches with 7 significant digits, then you will kind of say, I'm bullshitting because there's no way I can know it up to that. So I should probably, if the instruments that I have are just my hands, then I should just probably say, okay, I think it's maybe roughly 4 feet. I don't know. So sometimes like maybe there could be an illusion of precision where you have like so many sophisticated models, etc., for things that you don't really know. Other comments? Anything? Yes.
One of the things that I saw in a few of these that I thought is interesting, that it's like it's not what you hear about in the news, is that a lot, like so much more of these like exponential rates that we're seeing are because of software improvement, and that like. And how software improvement fits into like recursive self-improvement. It's not just more investment into faster hardware. I just found that interesting because it's not the phenomenon there.
Right. So in terms, I think there is basically we're seeing exponential improvement in AIs, and these are driven by several different trends. And I think maybe the general media kind of confuses all of them. One is, computer hardware is growing at an exponential rate due to Moore's law. Then potentially GPU flops might be growing faster. Then the amount of investment that we invest in hardware also grows. So the amount of flops available for us can grow. And then and then on top of that, there is a significant chunk of basically what some of these things call software. And software is a little bit of a term that can mix a bunch of different things, because it's not just kind of traditional software like coding, and it's also basically people doing a lot of experiments and machine learning research to find out more efficient way of doing the same thing that they did last year now at a better rate. Other kind of comments, responses to the reading? Yes.
My one problem with these papers is that like they seem to be really comfortable with extrapolation. Like, obviously, I think there is some merit to it, like scaling law kind of worked so far. There's also like Moore's law that's kind of worked so far. But like, I think with stuff like AI development, I think personally we should be more cautious about extrapolation. Like, sure, there's a trend that like AI is developing really well so far, but we know absolutely nothing about whether we are gonna hit a bottleneck that somehow just like whether we're gonna need another algorithmic breakthrough to take us to the to further like to better capability, or if it's just, like simply just a problem about scaling. So I think we should be more cautious about that.
But on the other hand, like, is there anything else we can do other than extrapolate when we're trying to predict?
But I think at least they should entertain the possibility a bit more that, like, we're resting on the assumption that as things stand, if AI is purely down to the scaling of multiple aspects, then that's how it is. But there's always a chance that better algorithmic advance is required for that to keep going.
Yes. Yes.
Yeah, I guess like the paper also, or these papers that like to kind of assume like no like regulation interference. I remember in the first paper it's like this is like the most frictionless environment. Like what's like it's like really giving you the maximal upper bound, and I feel like it'd be nice if we could also get like a lower bound, because like I feel like upper bound without knowledge what the lower bound looks like, kind of like it would be nice to see what the spread could look like in the future.
But maybe the lower bound is just at nothing. There's
just
zero,
nothing,
zero advance from right now. Other comments, and I don't know if anyone wants to say if they particularly liked one of those documents and found it more insightful. You can always also say, like if there is one of those documents that you found least insightful, but it's always better to say nice things. Any other comments? Okay, I mean, do you have comment? No? Okay, so we can continue. I mean, you can also just say later if something comes up. So, one thing that's interesting, like if you go to AI in 2030, then it makes this sense that basically the way to extrapolate current trends is to focus on compute rather than software improvements. And the main thing is that basically they say they follow kind of the bitter lesson, and the idea is that ultimately the methods to improve AI is to find simple ways to just put a lot of compute improvements, and then in this sense maybe you just focus on computing. But then if the picture is really not human ingenuity building AI, but basically compute building AI, then maybe it means that AI automating AI research is not going to give us that much lift, because maybe we are slightly inefficient right now in humans at using compute, but ultimately the compute is the thing that matters and not necessarily the AI. Although, again, like the true equation is probably something like, maybe the true equation is something like, natural resources or any kind of resources leading to energy, leading to compute, like in terms of flops, leading to, let's call it intelligence. And maybe there isn't like much cleverness to map computing to intelligence, but certainly we are not necessarily optimizing how many flops we can get per energy, and maybe not optimizing how much energy we can extract from the sun, or etc. Like obviously we could do the Dyson spheres, etc. So this lecture is really about like the question of recursive self-improvement, and if we kind of go back to this meter paper that I mentioned in the first lecture of this class, then this basically was some kind of a trend that we've seen that there is a certain doubling time, roughly every 7 months, the models double, can solve tasks that take human double the time that they could before. And if you just kind of extrapolated this I asked GPT-5 to extrapolate it, and if you just extrapolate it, and assuming GPT-5 did it correctly, then this is basically the trend line that you would expect. So maybe by 2027, you will get, by the beginning of 2027, you will get like basically a computer that like AI can do a full day of work, 8 hours, and then by 2028, you can, I mean, this says 1.2 days, but maybe if you thought about it as basically, so I don't know, it's 1.2 is like 30 hours or something like that. So you can think of it as, I don't know, 4 work days or something, or something along those lines, and etc. So that's kind of would be maybe the first most natural approximation that we can ask. But the main question with recursive self-improvement may be by applying AI to the task of building better AI, you can get something like this, right? You can get something that basically, at this point, the AI can do a day of work, and maybe you can start just using it and having like the effect of having like many more people working on AI. And yeah, we don't really know the answer to this. And part of what I kind of realized as I was preparing this lecture is that it really relates a lot to this lecture that we're going to have later on economics of AI impact. So the economics question is generally like what would be the impact of AI on the labor market and how soon or fast it will replace humans. This is basically specifically about the humans that are building AI systems and what happens if AI replaces them and how much productivity increase it will cause. So maybe looking a little bit at the questions of economics and growth theory makes sense. So I try to basically learn, so I'm not an economist, probably some of you are econ majors or maybe even econ grad students, I don't know. Is there anyone here that's an econ concentrator? Yes? Okay, so you'll have to stop me. Is there any PhD or any? No? Okay, so you'll have to correct me if I'm getting things wrong, but the way I view it is, okay, so let's try to kind of define something like the intelligence at time t. So it's very obviously not something that we can really put a number on, but one way to do it is to follow meter and say, okay, let's just call IT the meter task duration that AIs will be able to do at time t, and we can fix the parameters to make this constant. Let's say, AIs could do this at 50% chance, and let's say we'll give them whatever amount of energy and wall clock time. Let's say they have an hour to do it, and they can they can have like a certain energy budget, and we can just measure intelligence at this time. Yeah, the level that we are talking about is probably not matter so much how we define it, but let's just say that however we define I of t, we'll, like the meter, we'll imagine that it probably grows exponentially. And the main question that we are going to ask is it going to fizzle out and stop growing exponentially? Is the exponent going to grow, or is it going to go even farther beyond that? So some options for if you model how IIT is growing. So one option is that at any unit of time, intelligence grow by a constant rate. So this is basically growth is constant. Another option is that intelligence kind of compounds. So the more intelligence, the more growth. So at the unit, at time t plus 1, you grow by some factor c of the intelligence that you had at time t. And another thing could be that maybe you even grow more in less time. So the intelligence at time t allows you to not just grow by this constant factor, but even do it in a time, say, not just in 1 unit, now you can do it faster. Maybe the AIs work faster, they can do the same work that the humans could do, but now can do it faster. Yes?
I mean, don't we have like a fairly good analog to this of this human technological advancement in general? And as like more humans get getting educated, more research institutions and more companies that did research shows up in different areas, like the improvement in different areas within technology in the last like 150 years has only been possible due to the things that came before, but in like absolute amounts of improvement, you could say like surpassed the amounts of new things that were being generated. Like the amount of things that were being put out every day by humans is much more. And like if you look at like trends, it seems to follow like a accelerating scale, right?
Let me hold on to this question, because this is exactly the question that basically growth theory in economics asks, and we'll talk about it pretty soon. Maybe in like 3-4 slides, okay? So just these kind of things, like whenever you see something like that, like a recursive equation, like I at t plus 1 equals I of t plus c, it's basically a differential equation, right? Basically, the first thing is basically the derivative of I at time t is constant, right? Per unit time, you add c. So what's the solution to this differential equation? What? Linear, yes. Yes, right? And the second differential equation is di dt is ln c I. And since I see you are shy, I'll just say that it's exponential. And the third differential equation is basically what does it mean? Like you basically divide by like now it's not unit 1 at the time, but it's unit 1 over IT. So when you divide it, it's like basically I squared. So you basically have like a differential equation of the form some constant times the derivative of I is some constant times I squared. And this thing actually explodes. Basically, this means you get infinite progress at finite time. So this is like a true singularity. So basically, it depends on how you kind of model what you depends on how you model, like how much the fact that you achieved a certain intelligence allow you to keep progressing in intelligence. Then you can get exponential, you can get polynomial or linear. Like say, if the power here was so basically, if the power here is less than 1, you'll get polynomial. If the power is 1, you'll get exponential. If the power is larger than 1, you'll get a singularity, like it will explode. And one way to think about it is maybe that means that the power has to be 1, but you can also try to think about some other. So let's kind of make some observations that economists have made. So one thing that economists have noted in the context of various settings is Baumol's cost disease, which basically is the importance of bottlenecks. So once one sector of the economy becomes more productive, then in some sense, then what matters is the sectors that didn't become more productive. In some sense, this could relate to AI automation. Maybe AI will make some things, some parts of improving the AI more productive, but then the bottlenecks will be in other parts. And this is my understanding of it. Again, if someone knows this better, please correct me. So the thing is, like, let's just imagine an economy where there are only 2 types of people, farmers and non-farmers. Let's call them teachers or whatever. Like, so you can only do one of 2 things. Let's say everyone is perfectly capable of doing either one job or the other. And let's say originally, like basically each one of them earns $1 a day. Farmers produce 6 meals a day. Each farmer produces 6 meals a day. So each farmer can produce enough meals to feed them and one extra person. And if each one of them has 2 kids, the teachers each teach 4 kids a day. So basically all the kids get taught, all the people eat. And each one, so if it's an economy of 10 people, then there are $5 contribution to the GDP or of a daily GDP or whatever. So half the contribution comes from farmers, half the contributions come from teachers. But then someone discovers some kind of a great innovation that makes farmers 5 times more productive. So what will happen is now each farmer can produce 30 meals a day. And let's say it changes somehow what they get paid, maybe less or more, it doesn't really matter. But if every person can choose to become either a farmer or a teacher, and let's say they just will go to whatever pays them more, so the salary will have to balance, and so the teachers will also earn X dollar a day, whatever the X is. And now we don't actually need, in this economy, people can only eat 3 times a day. We don't actually need all that food. So what will happen is basically this sector that became more productive, there would be fewer people in it. And that means that the sector also, a fraction of the GDP has actually shrunk. So now if before, when farmers were less productive, when farmers were less productive, then they accounted for half of the GDP. Now they only account for 10% of the GDP. So in some sense, the sectors that become more productive are becoming, in some sense, less important in the GDP. Was there a question?
Oh, I was saying like that's probably why GDP is not the greatest market for this.
Yeah, so sometimes like you could see like things not necessarily showing or directly like the GDP might. Yeah, no. Another thing that we see from economics is this kind of very strange puzzle, which I don't know the answer to, and I'm not sure if anyone knows. And this is this puzzle that if you look at actually like the growth of the US in terms of GDP per capita, then basically for the last 120, maybe 150 years, it's basically been constant, 2% per year. And I don't think we have like a very good explanation of why this has to be like 2% per year. And notice that this has been through, electricity and the internet and cars. And throughout all of this time, and basically GDP has grown in the US 2% per year. Now this graph is not like this is not that if you take any country, then you will see 2% growth per year. Obviously some other countries you've seen like much bigger growth. But one way to think about it is that the USA may have been like basically at the frontier of global development. And the frontier has basically been going at 2% per year, even if some countries that are below the frontier, they could grow much more. Maybe they have more headroom. And I think it's a puzzle. Like, I don't think anyone knows precisely why it is. This graph is taken from like a paper by Chad Jones. I talked to him actually over the weekend. He also doesn't exactly know precisely why this is, and I think if he doesn't know, nobody knows. And one of the things is that we had this exponential rate of growth, and it's not completely, and it's a growth per capita, which is. So it's not just total growth, but we don't completely understand why this is the case. Although he does have a theory that can kind of replicate some of those things, and probably maybe it's the best theory that we have. And I just should say that like if like a lot of the time in this, I think in the literature on recursive self-improvement. People talk about basically people talk about GDP growth of 100% per year, or completely singularities. But I think if the GDP growth was 5% per year, on a sustainable basis. Definitely, if it was 10% per year on a long-term basis, like say for a decade, it will be a very, very different world, very different thing than everything that we have witnessed in the last 150 years. So even if AI, say, doesn't have like super exponential growth of like the GDP per capita suddenly growing like one year it's 4%, the next one it's 8%, the next one is 16 and whatever. Even if it just kind of lifts, in some sense, the number of 2% to say 5%, 10%, it would be like a dramatic thing that like nothing that we have seen in the last 150 years. Yes.
Have you seen like historical? I mean, I'm sure there are historical predictions on how things that happened in that timeline would have affected GDP and whether they played out as well or not. And so, it could be interesting to like maybe look into how much like of a GDP explosion people were predicting. Though I feel like there's like due to our culture today, there's a more of a culture of maybe exaggerating things. But like, do you have any knowledge of like predictions that were made within the last 100, 150 years?
I don't. I might ask Chad, but I don't. Yeah, I think it's just remarkable that this plot has been so kind of stable and I mean, one kind of similar graph that we are familiar with is Moore's law, but there is a much more better kind of explanation for Moore's law than I think for this graph, which is that, I mean, maybe there is some explanation for this graph as well. So maybe let me say that. So one explanation for this graph, one explanation for Moore's law, which I find compelling, is that Moore's law is not so much a prediction as much as marching orders. So basically, once Moore's law held for several years, then basically the semiconductor industry was forced to follow Moore's law, which means that there would be like a lot of investor, say, loss of confidence if they didn't follow Moore's law. So they basically had to. They didn't need to kind of invest too much in R&D to go above Moore's law, and they didn't. But they tried very hard in inventing new technologies to make sure that they still keep pace with Moore's law. And indeed, if you actually look at how Moore's law came about, like there's basically some kind of like 8 different, I think, technical breakthroughs and discoveries that helped sustain this. And maybe the Federal Reserve is doing something similar, like basically 2% per year is what we need to do. And we get really nervous if we go under it, but we don't, if we don't need to kind of work too hard to get over it. So maybe there's kind of some self-fulfilling expectations here. Yes?
Given that you mentioned Moore's law, I wonder if the semiconductor industry even was only progressing because of financial incentives, because there are other industries like high throughput cell sequencing for like computational biology, where you can like read cells out. They are actually going faster than Moore's law.
Yes.
Like the amount of cells you can sequence for RNA and DNA, it's way faster than Moore's law.
Yes. Interesting. So maybe it could be the case that if like that Moore, maybe it's the case that Moore was a little bit pessimistic and the semiconductor industry could have gone faster, but basically once they got it, they kind of said, okay, this is what we need to hit and we can hit it and we can invest in R&D exactly in the time, in the sense that we can, and we could have gone beyond it. I don't know. Yes?
I mean, isn't this a little bit of a cynical view of like Moore's law though? Because if you could hit it faster, then you should hit it faster in a capitalist economy like the American economy, right? Because then you can put your competition out of business and make lots of money. So
Yes.
this is the natural result. So if they could do it, they probably would have. So maybe a more optimistic view is just that, you know, the recursive improvements fall, and on a macro level, the recursive improvements in one sector fall onto others, and so the whole economy grows like this.
Yeah, I mean, I don't know. Like, it's a good question, but it could be the case that in some sense, like you invest, you regulate like how much you invest in. I mean, obviously, like if the researchers had like a better way, they like nobody would. I don't think anyone in Intel would say, let's wait. Let's sit on it and wait. Like even though we can do better, just because we are not due for like an update based on Moore's law, but it could be the case that basically they get more antsy, like more like lighter hand on the trigger to approve more experiments and try out more things and invest more in when they are like see a danger on the horizon of the current method that they're doing not being able to keep up, and they see. So I don't know. Yes.
So you mentioned something when you talk about like the transistors where like there are like 8. I think you said.
Yeah, I don't remember the number, but there were like a bunch of different.
Number of, like,
yes.
technological advancements.
Yes.
The reason why I mentioned that was I feel like with a lot of like the discourse around just like scaling and repeaterless and everything, people see like there's like some sort of retrospective studies that we can do where like maybe we just give more compute to older architectures and then we can compare them and we see that sometimes they do perform better than we expected, but also like newer architectures outweigh them in different ways. There are architectural advancements that we have made that have just made things much more feasible in general. So I feel like like the approach or like the importance given to algorithmic advancement is like somewhat downplayed. Kind of like what Asha was saying. Looking at like the other industries or like the microchip industry as well, and like with your AI knowledge, would you like agree, disagree? What are your thoughts on this?
I mean, I think there's definitely like algorithmic advances have been very important to keep up like with like you could, like I said, like, you couldn't explain how the AI kept up based on only on like the hardware available. So algorithmic advances definitely without algorithmic advances the AI models would not have kept up with the kind of pace that we have. Whether these things are, you'd view them, it's always kind of a matter of the beholder, whether they are kind of inevitable, where you have more compute, you can experiment more in how to more efficiently utilize your compute, and then you'll modify your architecture to take more advantage of it, and therefore you'll keep going, or maybe there is more fundamental things. It's kind of like really in the eye of the beholder. Right? So in any case, this is kind of like a question. And one kind of theory by Chad Jones on like why growth is like that says, okay, it's the question of like why do economies grow? And one answer is because populations grow. So populations grow exponentially, so maybe economies grow exponentially, but then why should they grow per capita? And Jones' answer is in some sense that when you have more people, you have more research. And when you have more research and you have more ideas, and the important thing about ideas compared to, say, physical goods is that you can share them and you don't have less of them, right? So, if the population grows and so there are more farmers, they produce more food, but they also people eat more, so it doesn't really correspond to growth per capita. But if someone comes up with an idea of how to improve the productivity of farmers and make them be able to produce, say, twice as much food that they did per acre, then this one idea can be used by all the farmers. It's not that one farmer uses the idea and then no one else, it got wasted and you cannot use it more. So this one idea can improve the productivity of everyone, and therefore you can grow per capita. So Jones kind of turned this into basically some like this kind of differential equation, where let's say A is kind of the growth of ideas, or you can think of it as like the total factor of productivity. So this is kind of the factor that says how much you can translate resources into productivity, and I is like the inputs to this. Let's say the number of researchers that are working in the field, and the number of researchers could be basically the number of researchers basically might be proportional to the size of the population, but there could be the case because there is some constant there, like that it doesn't that basically as you have more researchers, maybe you pick the low-hanging fruits first, and the other things become harder. So you might have the contribution to A might not be linear, but might be I to the lambda, where lambda is a constant smaller than 1. And then one thing you can say, the following thing, like just if you kind of write this down, then let's just imagine that both of these things kind of grow exponentially. So if A grows exponentially by a growth factor GA, and I grows like by a growth factor GI, then we know that the derivative of A as a function of t, ignore constants, so it's going to be e to the GA t, and and this is going to equal to g to the 1 minus beta GA t times e to the lambda t, and we subtract so if we just subtract this out, so if I divide this out, so we should get that 1. Is that the right thing? So we get that 1 is equal to. Okay, I'm always bad at this at doing math. So let's just So we take log. So we get GA and divide by t. So we get that GA is 1 is equal to GA minus beta GA plus lambda GAI. And therefore GA divided by GI is equal lambda over beta, which, nicely, is actually the thing that I wrote there. So, yes, I'm always bad at these things. But by the way, this is kind of like, I don't know, in all of these growth equations, I'm also bad at solving differential equations. So in all of these growth equations, basically the way I do it is I imagine that these quantities grow exponentially and then figure out if the math, like what the constants of growth will be. And if the math doesn't make sense, then they didn't grow exponentially. So then you know. Right. So in this case, like basically what it means is that the growth in productivity kind of goes like I to this R, the lambda divided by beta. And generally, if R larger than 1, and we kind of assume that as you go in productivity, say in AI setting, then you can also produce more researchers in terms of AI, that could basically lead to explosive growth. And then basically you'll have like super exponential growth, where basically the more research you do, the more AIs you do, they produce more ideas, and they produce more and more ideas, and then they become more productive. Then you are more productive, you can produce more AIs, etc. But even if you don't have explosive growth, I would just say the following thing. If we really do buy this thing, that main basic reason why economies grow is because population grow and because you have, and because when the more the population you have, the more people you have that discover ideas, then you can see that if you automate the discovery of ideas, like if you have more virtual researchers, that should increase growth. And so there is no law of nature that says growth needs only to be 2%. And like regardless of explosive, like I think when you look at that, there is really no reason why AI couldn't increase growth by a significant amount by basically increasing the number of people that are discovering new ideas. And even if it balances out on some different plateau, that plateau might well be higher than 2%. And that will be a very different world than the world, very different economy than the economy that basically you your parents, your grandparents, your great-grandparents. I don't know how many generations you have to go before to go back before 1880. So basically, like, regardless of the question that we are dealing here with this lecture of like whether we can do recursive self-improvement and whether we can kind of have like growth that is not even by any number, I don't think anything that we know contradicts, say, AI leading to 5% growth or 10% growth. And I don't think anyone, have not heard like a good argument against it also. Anyway, let's kind of try to imagine like what, if we wanted kind of to try to write an equation like that for AI, one way to think about it is, okay, what are the inputs to AI? So you can think, okay, the input is one is compute, another these kind of ideas, algorithmic techniques, and the third input is data. I don't know if I am missing anything. Feel free to say. And let's make a very optimistic assumption that we don't need data. That, like maybe, yeah, I mean, and it's not completely crazy. Maybe you could say, okay, like maybe we can replace data with compute like AlphaZero did, and just for the sake of like trying to get like, and just to remove one number from the equation, let's just kind of imagine that we don't need data, or we collected everything. And this is an optimistic assumption, so I'll just note that. And I also kind of want to mention that it's not necessarily the case that if we have more AIs, we can just kind of crank out and produce more and more ideas. Because ideas really usually kind of are sequential in nature. Like people, like they say, you know, you're building on you're standing on the shoulders of previous researchers. So ideas are kind of necessarily sequential. And also ideas involve experiments, like observation from the outside world. Even computational experiments take time. Yes?
I'm curious if like, almost like diversity of AI matters. Because I would imagine that there's like, you know, two of me can probably do double what one of me can do. But if you have like 100 me's, you know, you've kind of probably topped out.
Right.
In terms of like the unique ideas that I'm going to have. So I wonder if like this could become a problem with AI because we only have like 10 frontier models. Maybe like each one kind of peaks out.
Yeah, I mean, this is a good question. I guess the question is also, like, if we think of a model, do we think of it as a single researcher or do we think of it as a population of researchers potentially? Like, I mean, obviously, say ChatGPT can emulate a lot of personalities. We don't know if it can really emulate like a lot of diverse ideas, but it's potentially the case. But one thing that you're right, that this might be not enough to just clone one researcher. You want to basically have like more diversity, and we don't necessarily know if we'll get it. But it's not clear that you need different models for that. Maybe the same model, after it manages to do everything that one person does, you scale it more, and it can do 2, 4, 5, 8. So, but I just kind of want to say that, like in some of what below, I'll ignore this thing that is probably very important. That basically you cannot speed up wall clock time arbitrarily when you're generating ideas, because ideas depend on previous ideas. And obviously, if you're talking about science that is actually like the AI 2030 in the reading, it talked about like the difference between desk science and lab science. And lab science requires actually input from the lab, so that slows things down. But even like if you're talking about AI R&D, it's kind of intermediate. So it's not like proving math theorems necessarily that it's completely on the desk, because you actually have to run computational experiments that could take time. So you cannot speed up wall clock time independently. So we're making some kind of optimistic thing that we are ignoring that part. Another thing is that some of these kind of discussions basically assume that we are going to just build just focus on AI to build AI, and we don't need it to be good at anything else. But this is in some tension with our optimistic assumption above, that we imagine that we can drop data, because if you're also using it to generate data, like if you want this like model to answer, like if the AI researcher is eventually going to build models that are also not just themselves just good at AI research, maybe you want more data. And generally, like it could be, like AI research is maybe more than just coding. And so let's just try to kind of like model it like very, very naively. So maybe the simplest kind of, this is the simplest thing I could think of, but yeah, I'm not an economist, so maybe other people can find better things. Like I say, okay, let's imagine that like the derivative of, so this is like common in economics to kind of a production function. This is, I think, known as Cobb-Douglas, that you say you have like these two factors, and they are not completely interchangeable, so there are diminishing returns. You cannot just kind of split, have like more compute replace intelligence or vice versa, so you have like some kind of a factor like that. Like so, the derivative of the intelligence as a function of time is like some power alpha of the intelligence and some power 1 minus alpha of compute. So if you do that, and let's assume that compute is kind of grows like as itself as some constant depending on intelligence. So maybe as we have more intelligence, maybe we know how to do compute better. So let's again do the thing that I like to do. Imagine that they both grow exponentially. So compute goes with factor GEC and intelligence goes with factor GI. Then what we see is, okay, this equation, this equation basically says, okay, the growth of compute is C times GI. And if we plug this above, then we say, okay, so we get like that GI, so we get that GI so how did I get that, this thing? I forgot. I did this math and then I forgot how I got it. So yeah, we take the derivative, so we write GI equals GI to the alpha plus 1 minus alpha times C times GI, right? And then you move this thing, so you can divide by 1 minus alpha, you can divide by C, you can divide by GI, and you get the equation C equals 1. So what does it mean? The only way that it will grow exponentially is if intelligence and compute grow together. So there are basically two options. So either C is less than 1, compute goes kind of slower than in the intelligence, and then this will be kind of polynomial growth. Or C equals than 1, then they basically grow together. Or C is larger than 1, and then you'll basically have a singularity. You'll basically explode, and in finite time, you'll get like an infinite progress. So maybe this means that kind of like under these kind of very naive things that they will basically just grow exponential at some pace together, intelligence and compute. But this is just one intuition. So this might be some intuition for like kind of exponential growth of in the limit, the stabilizing at intelligence and compute going together at some exponential rate, which is unknown. Any questions? Yes.
I was just going to say, so I was running this in the background more specifically, but I feel like with stuff like this, there's like the type of intelligence that's required as well, and I feel like the growth that we look about that type of intelligence is somewhat important too. Like, for example, in the Bitter lesson, like it's not that he's saying like your students saying we shouldn't invest into algorithms at all, because he's more to say that we should invest into algorithms that take better advantage of compute, right? But we still need algorithmic improvements. So I was saying, considering perhaps like instead of looking at the performance of models on things like unrelated tasks, looking at the growth of model performance on tasks such as low-level kernel optimization, chip design, and things like that could give us like a more better like trend for the growth in the future. Would you like what would you think about that?
I mean, we'll talk yeah, but this is kind of like an interesting question, like say, which I'll talk a little bit later, but this may be good to talk. So imagine that you have a bunch of different tasks that you are a bunch of different tasks that you're trying to do as part of AI research, but what meters seem to have shown is that many of them kind of grow together in similar doubling rate. In the terms of absolute rate, they differ. So you might have like some tasks, like maybe in absolute terms, if you compare, say, human performance to model performance, models might be better right now at writing Python code than they are at, I don't know, chip design, and maybe they are better at, so compared to in absolute terms, but I think the doubling rate so far has seemed to be kind of similar. So in terms of senses, maybe the growth rate is kind of similar. So maybe here is kind of just another kind of model of automation that one can take is, let's just kind of imagine that there is tasks that people do. And you can think of these tasks as optimizing a kernel, writing Python code, brainstorming about a new AI architecture, I don't know, finding good jokes to put on the company Slack, whatever tasks that are crucial for the, for the improving the productivity of the company as a whole. There's some kind of distribution of these tasks. And what do we mean by distribution? Let's say that the distribution is basically maybe the length of time that these people take for these tasks. So maybe sometimes you do like a big project that takes you a month, and sometimes and you cannot really decompose to clean tasks, and sometimes you maybe do tasks that take you less. And maybe we can say that typically people cannot really handle a big task if they don't decompose it to small tasks. So on average, they complete one task per day. So maybe you'd imagine that very, very long task would be a very small fraction. And nobody that works on something that takes a year unless they manage to kind of break it up to discrete pieces that takes a shorter amount of time. But anyway, you could say it's some kind of a fat tail distribution of the tasks that people do in this company and the length of time that it takes them to do that. And now, making a very kind of strong assumption, let's say this kind of captures the complexity that it takes for AI to do it. And this is basically like the duration, like meter captured. Then maybe what you could imagine is that basically as AI progresses, it starts picking off more and more of these tasks. It starts basically automating more and more of these tasks. And basically, so you have this probability distribution, and at time t, you automated all the tasks with complexity less than IoT. And so at time t or t star, like you automated everything up to here, and you didn't. And these are the things that humans are still doing. And if you kind of model it like that, then the fraction of non-automated tasks will be like 1 minus the cumulative distribution function of this probability distribution. And if it's some, so now if this thing grows exponentially, if IT grows exponentially and P, let's say it's some heavy tail distribution, then actually what will happen is that the fraction of tasks that you didn't automate at time t decreases exponentially, which actually might mean that you'll probably go maybe pretty fast from automating half the tasks to it kind of really depends on precisely like the tail of the distribution and all of that, but like you might kind of be going pretty fast from so you might expect that, say, if you like automated half the tasks, then maybe in 7 months you'll automate 3/4 of the tasks, and then in another 7 months you'll automate 7/8 of the tasks, etc. Yes.
Can you elaborate what the heavy tail means?
So just generally, like we probably like generally probability distributions, and there are kind of two general types. Again, I guess, okay, let me just say generally that generally think that there are only basically two functions in the world, polynomial and exponential, and everything else is just a hoax perpetrated by the Chinese. So I don't really believe in other in other functions. So probability distribution, it can decay like any probability distribution kind of looks like something like this, or if it's positive, then it looks something like this after you send and it has to decay, right? Because it has to sum to 1. So the probability has to decay as you go farther and farther from the mean and the mode, and also like I think also like distributions like we will center it, and distributions that are the mean is different from the mode are also like a hoax. So it has to decay in some way, and it can only decay either like a polynomial or like an exponential. If it's an exponential, then in some sense, like it's basically like finite. Like at some point, it's so small that you can ignore it. So then, basically, at some point, you obviously automated all of the tasks. If like that, if it's exponential, and if it's polynomial, that's kind of the hard. That's the heavy tail case, where it decays slower. So that then you want, and then basically, but even then, if we assume that the meter thing kind of works and that the complexity of tasks that you can automate kind of doubles every time, then eventually you'll get all of it.
So for both cases, you have the mean at the same point, but then just the way they indicate.
Yes. So heavy-tailed would be kind of like polynomial decay, and non-heavy-tailed would be exponential decay. So like the normal distribution is not heavy-tailed, right? It's like it decays like e to the minus x squared. Okay, maybe before so this is kind of maybe like some expectation of how you might think like the fraction, like how a meter thing would translate into the fraction of tasks that get automated within like a company or a person or profession.
This assumes though that the tasks remain static and you don't get new.
Yes, this is a great question. Like this assumes kind of the task remains static and people don't change, which is obviously false. So obviously it's a little bit like Bauman's cost. This is what will happen is like when you're here, you'll probably like have all of the humans start doing these things, and maybe suddenly they managed to do things that were out there way before they would have taken like ages and nobody was actually doing. So you would be automating what the company did in 2024, but now it's 2026 or 2027, and they're doing different things. So it could be the case that it's basically always the setting that but it might also be so it could be the case that we are for a long time in this hybrid mode, and it could be the case that at some point humans cannot keep up, and these tasks that are way out just have to, even with the assistant of the AI, maybe the AI is too advanced for the humans to take advantage of it, possibly. But it's also quite possible that forever it's the case that we basically do more advanced things, and the humans find way to take advantage of AI and provide their own added value. Yes?
So I think we could say fraction of non-automated tasks diminishes, but assuming that more complex tasks will take like longer time, maybe linearly with the complexity, does this have any implication of fraction of non-automated time? Like
So basically, if we kind of assume that non-automated tasks, like say the fraction of non-automated tasks is something like 1 over the time, then you would assume that basically and you assume that the length of time that AIs can handle grows exponentially, then the fraction of tasks that have not been automated yet will decrease exponentially with time. So basically, every time there is kind of a meter doubling, there would be a halving of the tasks that you have not automated yet.
But let's say you automate the percent task, right? So maybe even when you automate 75% of the task, you could only be saving like 2% of the person's time.
Yeah, I mean, yeah, it could be the case that, if once you average it over time, then it's different. Although, like, I think eventually it will catch up because of this exponential thing. Maybe here and then, yes.
So most of the time, and I economics, you measure productivity not just in terms of time, like labor, but also in terms of capital.
Yes.
The Cobb-Stubbock function takes into account capital and
Yes.
labor. So wouldn't this be less of a shock to TFP and more of a shock to the capital labor distribution?
Yeah, so that's a kind of a question I didn't go into. And I think it's even like a big question of whether AI could become, should be looked as labor or capital or something else. And I think it is not completely clear. And actually, Jones has like a very recent article where they kind of models possible ways with how AI could modify, and some of the models could actually keep the fraction of capital constant. But yeah, just generally, we assume that AI could potentially change what you do, like take things that before that. One way to think about AI is that it allows to invest capital to do things that before that could not. Make labor and capital more substitutable, because now you can actually build more, invest more in, say, energy to do things that before were labor. So one version of it is that it changes the distribution between labor and capital. But I think in the version that it basically corresponds to inventing ideas, it's kind of also does these other things. So I think it's a little bit complex to model. And some of it will be a great thing to ask the economists when they're going to give the guest lecture. Yes?
So I'm just curious, do we have models for like how quickly like the sort of front end of this moves as people adjust to new technology?
I don't know. It's a good question. So maybe before we take a break, is the group doing the experiment ready? Yes? Yeah. Yes? Good. So let's do the experiment presentation before we take a break.
Hello everyone, my name is Edgar.
My name is Dashel.
I'm Hannah. I'm Julia.
And we are the group that worked on the recursive self-improvement experiment. We kind of solved it, so I can wait for the GPT-6 announcement tonight. But yeah.
Maybe use the mic.
Oh yeah.
So for recording.
Hello. All right. So yeah, let's start with our motivation for our experiment. What we realized recently is that a lot of the researcher type of systems have been moving towards more multi-agent systems that work together, and even non-researcher systems under the hood work in like these complex different like systems where things flow to each other. Right? Nothing exists as like a single node. And especially in like some of the benchmarks that we see about research, we see that multi-agent systems are performing the best. So we wanted to experiment a little bit about how exactly the multi-agent system scaling moves forward. So the question that we had was, once we achieve models that can solve a task of some difficulty k, let's say, can we compose such tasks such that we perform tasks of arbitrary difficulty, and how much composing models in certain architectures helps us achieve higher performance. And do AI agents improve at RSA tasks by delegating the parts of the problem to submodels? This is like the signal so far seems to be yes, but we wanted to explore it in a way that tries to keep other variables constant, which usually is not how it's done in engineering contexts. And yeah. How will task delegation for AI research tasks look in the future? And what does it mean for alignment?
So we're making the assumption that when a company or institution tries to do AI, have AI agents speed up AI development, they'll probably try to use the benefits of organizational power. So you want agents not only doing things by themselves, but also working together in a structured way. And so our three architectures that we're comparing are one, just a basic agent that is working alone, so feed GPT-5 into some tasks. Second, coming up with something that we think is analogous to the hierarchical organization that humans have. So you have an agent at the top, and Eggy will talk a bit more about how we implement using Agent Bench, but you have an agent at the top who takes in a task of some machine learning engineering variety, and then tries to split it up into subparts, and then leaves at the bottom do tasks and get combined. And so this is the kind of the most hierarchical structured version of the architecture, compared to the default. And then the final thing is that we come up with this star graph architecture as well. And the idea of this is that you might have a bunch of agents that are working together in parallel, either because they've been delegated to do similar things at the same time, and then one agent at the top combines them, or because there's a bunch of different tasks that can be split up, but they don't have to be split up. And the kind of sort of trade-off that exists here is you have more leaf nodes at the bottom when you look at a binary tree, and so in theory more agents that are doing stuff, but then more agents at the bottom of the star graph, but then with the binary tree you have more hierarchical organization and planning incorporated. And we keep constant the number of nodes that are used in our agent setup to create I think we do 7 nodes for both binary tree and bench. Okay, so the tasks that people tend to care about for recursive self-improvement are machine learning engineering or research tasks, because those are presumably the ones where if you have AI agents working on them, they will improve most. I think the super ideal version of this experiment is to just run lots of stuff on rebench and get full benchmark scores, but we had a combination of some cost limitations and some time limitations. And we also wanted to test out some more basic machine learning engineering tasks, because what we found is that our agents are pretty bad in some ways at doing delegation and working together in workspace folders. So we come up with 2 different tasks. One set looks at identifying families of data sets, and then a second looks at doing classification with a set of latent variables. And so trying to both look at how well these different architectures perform, and then also can we just explore and see what's happening when they are working together in a workspace and doing things.
Yeah, a small thing about the task specification is, well, the one reason why we wanted to do that was because we thought perhaps under the dataset classification task would be a good analog for research tasks that are still humans are leading in, which is more open-ended exploration and thinking as like a researcher rather than just software engineering. But yeah, so we have an XKCD here, 927, which is my favorite actually. And it is how standards proliferate. And this was something that we just experienced quite a lot throughout our time of like working with agents. So that there are a lot of competing standards. Someone's like, oh, we should create a standard that unifies all of these. Like, this is ridiculous. And then they create another standard, and then there's 15, right? So this is the case it is right now with AI standards and agent evaluations as well. And that's just how it's going to be. So let's a couple of other technical details. So we started using line graph and LangChain for the agent graphs because we had some familiarity with those before. Also because line graph and LangChain allow a fair amount of state control. So what you actually feed to the agents and things like that. And then afterwards, for the evaluation, we used the inspect tool from the UK AI safety team, which funnily enough has its own like agents coordination like portion of its architecture. But rather than doing that, we just kind of like made like an adapter for the line graph portion. And yeah, we use Kaggle for the data sets that we got for evaluation. And before we move forward, I just want to lay out how exactly this information here flows. Our first root node gets the main task and is explicitly delegated to split it into 2 subtasks, right? And with the information that it will get split up into more tasks in the future. And each node knows where it is in the hierarchy on the tree. And what happens is that, for example, the node here that gets a task that's, for example, like writing the actual code for the training, it does not know what the higher level task. Like the entire higher level task that the root above it got, right? So there is like a clear hierarchical thing. It doesn't. There's like a stopping of the information flow. It just knows what it needs to do, and then it sends them back downwards. And then once it reaches the leave nodes start working on these things on a shared workspace that we created on our computer, so they can see each other's documents and can interact if they need to, and can have their own work desktops as well.
and then after they finish, they send the information back that they finished. And once all children have responded, an agent can collect all of those together to essentially create a deliverable for its own task. And then this goes up until the root response.
Yeah, so I'm going to talk just for a little bit about what we ended up seeing. Basically, so the first thing we did was we ran just GPT-5 alone, the star graph, and the binary tree on a medical data set. We asked it to classify.
I just want to comment that yes.
Yeah, we did it this way because we wanted to follow in the footsteps of people who came before us. That's why we also had like this logo in the beginning and everything.
See, okay. No, but it doesn't make any sense because when the numbers are bigger, then your bars are bigger.
You're so right. We kind of forgot about that one. Yeah. We still clearly have a lot
you have to learn to.
We'll fix that next time.
Yeah.
But we see sort of what we expect, like making the model divide up the task that it's given into subtasks does well. We see the binary tree and star graph do pretty significantly better than just like GPT-5 on its own, and the binary tree does slightly better. As a task, we think this is relatively like in distribution of things that the model knows how to do. All three of them opted for training a neural network on this data set. It was just to classify something or other. And the point is, but just like some interesting things that we observed are, for example, yes, the binary tree did a little better. The other thing that's
just one question: did you, when you say the default, is it best of 7 or what, or is it just 1? Because the binary tree and the start are using 7 calls to GPT-5, right?
Right, this is 1. So best of 7 would be interesting. I would have increased n just for general with more time. We're gonna just run this a couple more times and see, and we can take best of 7 just to.
We didn't
make the
control
evaluation.
for the compute, unfortunately.
Yeah.
The compute span.
But that would be interesting to see. But one of the things that is interesting is just with the way these divided the tasks. The binary tree had this is a depth 2 binary tree. At depth 1, these agents, maybe what we often saw is one handled preprocessing, one handled the actual making of the model or some division like this. Whereas for the star graph, most of the subagents are thinking about design, but most of the actual code generation and running ends up happening at the integration phase. So it's just interesting to see where each of these things happen, even if they both did comparably well on the problem. Though our bars make the difference a little more. And then for the other, for the other exploratory data analysis tasks, the first thing we noted is all of the models did sort of much worse than we originally had expected at the task. As in most of them failed to identify most of the data sets that we provided, and they were all relatively low Kolmogorov complexity, or simply generated data sets. And all of the models did not do too well at identifying what they were seeing. But we did get to see just how the models think about task splitting, and that was interesting. So for the binary tree case, we saw the root agent would maybe come up with 2 different methodologies of analyzing the data that they see, and then split that between the 2 agents. And the 2 agents would maybe run some tests, they would all write some code, and then ultimately it would come to some conclusion. Whereas the star graph, the way it sort of formatted its thinking was a lot more of the form of it listed out a bunch of things that the data set could have been. So it had one agent check a bunch of standard univariate distributions, one check a bunch of standard bivariate distributions, and then it just kept sort of running. And so it's very interesting. And then for the times that we could see, sometimes they came to the same conclusion, sometimes they did not. But we didn't really. We didn't have too many successes, so we don't have very good numbers here. But it's just interesting to see how they think. And just overall, what we saw in both types of tasks is when we have these recursive, low degree agents with few branches coming out of them, what you end up with is the agent comes up with different methodologies for evaluating the problem, and maybe tries them both out, and maybe combines 2 pieces of the problem. Whereas when you have one node with 7 children, it comes up with a bunch of the tasks it comes up with are a lot more rote. you end up actually seeing less work on the leaf level. But then, like, sometimes it will also perform better now because you're just testing. You have one guy for specifically testing maybe if it's Gaussian, maybe if it's like univariate, something or other. And so, because in some ways, this like branching performs different tasks. Like the thing we hypothesize from this is you're actually, and like what you would want to see in like a real recursive self-improving system is a combination of both. Like you'll have the ability to like at the top level take a task, split it into multiple methodologies, evaluate those, but you also need a bunch of like high branching, like maybe we have 10 options for what to do here, just try each one, and that like we really see a lot more in the like star graph than the binary tree graph. But again, like n is relatively small just because we ran into like quite a few computation cost tasks, so I would be very interested in comparing to best of 7.
You burned like $400 in maybe an hour. I was surprised they let me do that for rate limits. Like, I mean,
well, then they stopped letting you.
Yeah, then they stopped letting me do that.
Which you used our API, right?
Yeah, I mean, yeah.
You can always ask me to try to upgrade you the tier if you need.
Yeah, I want tier 3 because I spent like a fair amount this summer. But like, yeah, I could try maybe higher tier.
The money disappeared fast, and the rate limits were sort of shockingly stringent at the end and loose at the beginning. But
yeah,
this is mostly because we were just trying to run a bunch of experiments in parallel, and the API got very mad at us. Yeah.
Yeah, and I think something else we saw when comparing just like the kind of like ML model building task with maybe this other like data classification task, is that I think in general, at least right now, our agents were able to perform a lot better when they had like some sort of structured objective, right? So I think it's like, or at least to me, it seems maybe more clear how to like break down different subtasks if you want to like build, you know, a model, like a neural network, something like that. And maybe a little bit less clear when you are just trying to like do general exploratory, like problem solving. Right, so like if you're trying to do some sort of like clustering, maybe then it seems less obvious how to like split this up in sort of like a structured manner where each of your agents are actually doing something productive. And so this might be, you know, maybe like one possible barrier in terms of which tasks are most relevant for recursive self-improvement and where we can kind of see the most improvement when we kind of layer agents together in this way. And yeah, I think another barrier that we kind of saw is that, you know, the intelligence that these models have is still like a little bit limited, right? So like, you know, maybe something that we could have done is like spend more time on like prompt engineering so that they like maybe had a better idea or like a more clear idea specifically in like, you know, maybe like the clustering context of like what exactly to do. Right. And so the models in general were like not super great at like kind of like staying on task and like following instructions, and they maybe kind of veered off course a little bit, which I think is also seems like harmful to this kind of, you know, structure that we had where it seems a little bit necessary that all of the models do exactly what they're delegated to do. Yeah, and I think some other things that we saw in general was like basically the way that we set up our directories were like all of the agents would just like have access to like everything within the directory, and so this is like clearly not something that is ideal, and I think like in general when you're working on something that's like actually maybe high impact and like where it's important to maybe be more cautious about things like that, right, is you know, have like each agent have their, you know, specified like internal directory and like change the permissions on like everything else such that it, you know, they can't like access things or like basically read at other things within the directory, and stuff like that. So yeah, I think that's something to keep in mind from like a safety context. I think another thing that, you know, might be worrisome or like something to think about within this context, right, is that like as I think Ege mentioned earlier, like all of these children nodes, they don't really have access to like the higher level picture that the parent node is trying to accomplish. And so, you know, basically what this means is like maybe you have sub agents who are kind of like doing things wrong or like doing things that are probably like a little bit misaligned, even if their like original prompter has this like very good plan of like how to keep things aligned and like on track and like within scope, and things like that. So I think that maybe is like another interesting direction to explore as to how to ensure kind of you have this like big picture view that will still eventually come together at the end, even with independent sub-agents. And yeah, I think in general, right, I think it's probably likely that something like recursive self-improvement is able to achieve better accuracy or like better accomplishments at like higher level tasks, like ML research tasks at like, or like it's able to reach this milestone at an earlier stage than, maybe like a single very, very large like foundational model or something like that, just because of the composability of AI systems, right? So it seems natural to have some sort of like structure like this, where each agent kind of is able to do things that maybe it has some sort of specialization in, or like maybe it is just like has been broken down into like a simpler task that it is like more within scope or like in distribution for the specific model itself. And then it's like some future directions that we think would be interesting to keep exploring is just like in general what happens with performance, or like how do these agents break down into subtasks as the task complexity increases, right? So the tasks that we tested on were like relatively simple. So like, how would they deal with like writing an entire code base from scratch, training their like own LLMs from scratch, and things like that, right? So we already have, there's like, a lot of research that's like already been done on how like a single LLM really is not able to do well at like long context tasks. But, I think it's maybe intuitive to think that this, if you gave the same long context task to like a kind of like recursively built structure of agents, then this performance might be able to improve. And then another thing that might be interesting is like specializing sub-agents, right? So maybe you could have like one sub-agent that's like really good at like this specific engineering task, and another sub-agent that's really good at like, maybe doing something like science-y that's related to the task or something like that, right? So like kind of like at what level does it make sense to have this breakdown in capabilities between the sub-models? So I think something else is, we brought this up a little bit earlier, right? But what kind of alignment cost is there to task delegation? So like when we remove this like higher level context, specifically, how do we see maybe alignment within the sub-agents decrease, and kind of what is this trade-off between having better alignment and providing more context to the sub-agents versus having them like stay strictly in scope and removing that context from them? But yeah, everything from there.
Thank you. Other questions? Yes.
I was curious, especially for the like binary tree step, kind of deeper orchestration, how much computation you see happening at each kind of parent node, and how much versus the child nodes. So, like I can see issues where a parent says one of you should do the data processing, one of you should do the model. The function signatures are not compatible, and the guy has to rewrite the whole thing at his own.
Yeah. So what you end up seeing actually, like in the good case, it usually specifies out like the API on both sides, and there's actually not that much integration help.
Good.
When I've just been watching it run, it has happened that things have been incompatible, but usually actually the like top model like specifies how to do things right. So yeah.
And specifically for this, what will happen, for example, for data analysis that I've seen is that if one node is tasked with generating data and the other node is tasked with like writing the analysis scripts, the analysis script writing node will like generate some sort of its own like small data set, and I will make sure that it's compatible in terms of like this code and everything running. And then the real data set that's from the real other node will be run with the data analysis code at the integration phase.
Yes. So you said that the nodes at the same level shared like workspaces. Is that Did I cast that right?
All nodes share the workspace.
So it's the same workspace for all the nodes.
But they have subfolders.
Yeah, so
they're encouraged to work in their subfolders, but in theory access other subfolders.
They have on their subfolders, and there's a main like production folder where after they finish their work, they're supposed to put in like the final version.
I wonder how much like context you're like adding up just because every time like every like new fresh like instant every node has to like explore the workspace and like understand like what files are available there, and like you just pass the other assistants, let's say, or agents have access only to like the work product, right? Like not the context of like how the work product was created by the different nodes.
They have access so we wanted to keep some things open-ended because in the nature of the experiment. So, but we still forced certain things. For example, we forced that the agents that finish their task, once they like let their parent know that they finished the task, they also send out like a report, such like a summary of everything they did, and also they write a report onto the like file system that can be read later on. And when like the entire task is completed, there's like a final report created as well. But the idea is, once like the signal for having finished gets sent upwards, a small sentence or two explaining, okay, this file does this with like this framework, this file does this with this framework, or whatever, is sent upwards. And then if the agent above, like the parent, deems it necessary to read the file, it can just use like a bash command to read the file.
And did you find that, so if you think of the nodes at the same level working at the same time, like if one of them could cooperate with the other, it might be impractical because they're both starting at the same time, so they might have to wait for like the work product of one to like consider that. Like, did you find them waiting or like?
Usually the nodes at the same level are not communicating at all. Like this very rarely happened that they would. They would usually like write their standalone product, and then the integrator above them would be the only one reading.
They're explicitly instructed also to be able to do their work independently of whether the other node is finished.
I was gonna say, while developing this, I ran into this problem, and this was like a fairly simply solved, quote unquote, through like letting the delegators know that the tasks at the same depth will probably be done concurrently. So that's why. So they need to be done in a way such that the tasks can be completed independently, right? So the thing that I mentioned about like using dummy data for data analysis, that wasn't like emergent behavior. They didn't immediately decide to do that. It was only after that I explicitly instructed in the prompts, make sure that the tasks that you delegate to your children are parallelizable without them actually needing the stuff from each other, and then you can integrate them after the stuff has been sent back, right? So we did actually run into that problem originally.
It's sort of like on I think a related note, like let's say your like parent node, it's restricted by like the maximum of like all its children, whether it's like binary would be 2 or like in the star it's like multiple. So like, was it the case that like the children would complete like one takes like 1 second, the other takes like 30 minutes or whatever? Like maybe not that extreme, but that like you're bounded by like one process that's like just misdelegated because it's like much longer than it should be.
There has been times where like the parent just needs to wait for one of the children to finish and can take longer.
Like, is there like a large difference though between like the two children, or is it like the parent generally like has a good sense of like how to delegate?
It's a little task dependent. Like in most of the like in the ML year tasks, like if one handled pre-processing, one handled making the model, the one that would make the model generally took a little longer. I think what you end up seeing is it's really just a question of how well does the parent delegate the tasks. I think overall it did a pretty good job at making them take the same order, but that could vary. I don't actually have numbers on how much they varied. I could actually look at that.
Yeah, you could actually encourage them the parent to do that by basically saying like a model, like each model gets a timeout parameter, and if it doesn't do it in the timeout, it dies. So it's encouraged to basically, so the parent is encouraged to try to, if it wants to be, to get it within its timeout, then it wants to kind of balance things out and give a timeout that is somewhat smaller to...
These are your children, if they don't finish in time, they will shoot them.
did you ever, or did you force the parent to distribute the work, or was there ever situations where the parent just decided to complete the task on its own?
The parents were forced to distribute.
That said, they often, like, in the instances where I think the model determined it wasn't that useful, they generally just, like, they gave 2 small tasks, like maybe decide on a methodology for this and decide on a methodology for this. They waited and then just read that and continued. So,
yeah, like sometimes trivial tasks was given essentially in the same way.
Yes. So how transferable are the prompts from one task to another? Like I imagine if you have 2 different types of tasks, like one is like write this type of script, another one is like, oh, I want to create a model with some data. Like I imagine it would be quite a bit of prompt engineering to adapt the system for one task versus the other.
You mean system prompts or the task prompts?
Or both?
Well, I think the system prompts we try to keep as open-ended as possible. And so they mostly are about how to delegate the work, how the system is structured, and what is expected from the models. And yeah, just like good delegation customs, I guess. And the task prompt is, I guess, a different separate variable in that, like, however much the task prompt will need to change for different tasks for one agent, presumably will need to change at least that much for multiple agents here, or like on the order of that much.
It is true that you don't have agents at leaf nodes who are systematically better at doing one thing or another, and they're not given any sort of personality type. That would probably be an interesting variation, but in general, they're just supposed to do well.
Yes. Are the subtasks created by like a structured tool call, or is there like another mechanism? Like, are you running like an MCP or something to try to get the subtask creation?
it's technically a tool call, but it's line graphs like graph system. Right?
Yeah, isn't like it's more okay. Like if you think, okay, this is somewhat like library dependent. I think here it's structured output that gets parsed by the line graph like parser, and then on the line graph it gets sent to like the whichever agent will get sent to what is dependent. They decide on that. From like a model's viewpoint, I don't think there's like a big difference between the two, of like labeling it a tool call versus labeling it like a once you want to like, because these agents run in a loop, right? So once they want to pass on like the tasks and the information, they just output in like a structured format, and that structured format gets parsed by line graph.
Well, the reason for the question is because I would assume that OpenAI trains the models to use tools. So the quality of subtask creation might be dependent upon whether or not you're like utilizing that sort of training.
Yeah, but I assume GPT-5 is also at least semi-proficient at like creating structured output, right?
Yeah, outputting JSONs is also something that's very common. So.
Yeah.
Yeah, I find it like fascinating. I think would be also interesting. I don't know if you tried like maybe a weaker model like GPT-5 Mini or something where maybe this task, the benchmark would not be as saturated. Generally, I would be very curious if you had like an hypothesis of what the difference between star and binary tree is, but if you could kind of test this hypothesis by maybe increasing n and trying a bunch of different benchmarks and seeing whether there are benchmarks that where star is better and benchmarks that binary tree is better, and whether then you can try to understand if there are like certain type of things that this type of organizational structure works better than the other. Yes?
Parents able to re-invoke their children? Say like the parent wanted to try 4 methodologies, but it only had 2 children. Could it do like another round once the first round was done?
That is something to explore. Right now, what the parent will do is it will tell the children, okay, you need to explore 2, you need to explore 2. So you need to explore 1, you need to explore 1. But it's like a very much set in stone structure of how things work.
I think one thing to explore there as well would be to see if you actually need that much capability in the model as you go through the nodes. Like if you can dumb down the models or like have like less capable models as you enter like less intense tasks. So like the final task, maybe like 5 Mini could easily do it because it doesn't need all the context or the understanding of like what the big picture is. It just needs to like, write like 5 lines of code. So that could be interesting as well.
Yeah, that's definitely true. And it could be a good way of maybe keeping compute constant or closer to constant, right?
The other thing that we did want to try, but like it didn't make sense for an experiment, but if you were implementing something like this at scale, like in theory the agent should be able to call like a variable number of children, maybe say like I need a like 5 mini for the small task. I also need like a 5 pro plus plus max to like do this really hard thing. Run both of these and then so like if you're implementing this at scale, there's much like cleaner, more interesting things you can do. But right now we just want to compare like how it's polished.
Yeah, and I guess like from like a scientific perspective, we try to keep the constant as constant as possible and only vary one thing.
Okay, let's take a let's take a 10 minutes break. Yes. I think this could be like a very cool continuing project of a paper that we try to study. Like you have this hypothesis of what star versus like I find it like historical here. On improvement and yeah, some of these things are again like recursive self-improvement, like strictly speaking, is kind of a self-perpetuating loop where you get where basically like progress, instead of going exponential, going super exponential. But it's quite possible that you'll have some improvement that even if they don't go all the way to self-improvement loop. I would guess most people would say that progress has been pretty fast already. So if it's only kind of speeds up by a factor of 2, and that's it, like one time speed up by a factor of 2, that's also pretty fast. So even if like we don't completely, you don't agree with all the factors there, you should kind of remember that it's not necessarily a binary thing between no speed up at all to super exponential. So I guess I hope you remember from we read AI 2027 in the first lecture, and the story is basically that you have these agent 2 that run in. So in March 2027, you have like all of these agent 2 copies, and they basically keep updating themselves and becoming better, and they find like better ways to some algorithmic ideas, and eventually they train these kind of agent 3, and what they call is agent 3 is like basically superhuman coder. So what does it mean? You have basically, they basically assume that it's basically like 50,000 copies of the best human coder sped up by 30 times. And basically the idea is once you have this superhuman coder, maybe there is you might assume that if that the progress will be at least 30 times faster if it's like a human 30 times, and maybe more because I don't know actually under the prediction how many employees Open Brain will have by this time, but I'm assuming it's less than 50,000 by March 2027, but also because I don't want to spend all my time doing job interviews, and we have to hire this many people to catch up with the predictions. So you should be able to speed up by both having more copies than you have employees, and each one of them has 30 times. But basically, you still have there's still some slowdown. So they assume that like there's only 4 times speed up, and And then, like by June, you get to this point where they assume that basically you have like these geniuses in a data center, and basically I guess this is like every night you wake up to another week work of progress, and basically most of the time you don't do much, and most of the ideas are useless, and the predictions there in AI 2027, then basically on this is June 2027, which would be this thing, and it was 50,000. Okay, maybe I'm confused. Like, wasn't it 50,000 like in March before? Now it says 200,000. But anyway, the number of copies grows, and the number of the speed also grows, and eventually, like, it becomes basically the humans become completely useless, and then you have like these 300,000 copies that are 50 times the speed of, and you speed up compute by 50. You speed up progress by 50 times, which basically means you get like a year worth of progress every week. So let's try to kind of like look. This was the story, but they actually did like quite a lot of work on numbers behind this story. So let's go into the numbers. So the forecast basically has like two phases. One is what's called like a superhuman coder, which is an AI system that can do any coding task that the best AGI company engineer does, while being much faster and cheaper. And the second stage is basically once you have that, then you kind of start like the crank on recursive self-improvement. So let's focus on the superhuman coder. And they try to ask, when will we get there? And they had like this methodology where they said, well, maybe it should correspond to X amount of time on the meter benchmark when you're assuming this is 80% success. So basically think superhuman coder is when software engineers or ML researchers, when the model can do with 80% probability of success tasks that take X time for a software engineer. And the question is, what should be X in order to achieve that you do, like you basically can do any coding task that the best engineer does while being faster and cheaper. Let's forget about the faster and cheaper because things get cheap and fast very fast. But let's just say, what would X correspond to make sure that you can do any task that the best company engineer does? And maybe you can, actually, like the animation I did, but maybe before we kind of say what they did, maybe people here can say what would you think is the value of X? Any suggestions? Actually, let me give you, maybe this is kind of interesting thing. So let me give you like 5 minutes to discuss in tables. So what do you think would be the value of X? So if you got X on the 80% meter benchmark, when a model got to a level X, what do you think would need to be this level so that you basically get to the point where you dominate every engineer at OpenAI? So let me give you 5 minutes to kind of talk among yourself and see what you think would be X. And you can also come up and say, we think it's meaningless and X is infinite, or X, or like it's completely uncorrelated.
Yeah.
But the thing is also like, I have to wait 5 years. Yeah, there are a lot of 5 years long. Not necessarily because intelligence aspect that you have. And like, there are certain aspects that were like engineers can write down the certain aspects that actually know. But when it comes to I feel like I'm like probably kindergarten to with them. So like I think it's around this the time
like how hard is it to make
I'm saying the first class
I have no idea what you're talking about. Like, I mean, I'm trying like two like practical
Wait,
like fuck code saturated. Fuck code saturated.
what I'm saying is no matter what so it's definitely so I'm attracted to game learning. I'm just like not good at I can see quad.
I want to say the problem is and that's not the point where we have to it's getting slow sometimes, but sometimes I will and then like and also
So maybe like in 30 seconds we'll. I'll walk between the tables and ask people for their estimate and justification. We'll start in like 30 seconds and just kind of maybe also maybe I should have kind of thought of like try to ground, like you can imagine what kind of tasks like people might, someone might need in a company or something like that. You can maybe even think of something like, say, one thing could be, okay, you want to replicate like you find like a paper, you want to replicate the paper, that could be kind of one type of task. You want to you read like a training algorithm, you want to write code to implement this algorithm. You want to optimize, find like the best kernel, whatever, for like a given thing. So you can try to think of like what's the magnitude of like a task like that and what it would take. And of course, maybe at some point, if you can do these tasks at some point, like you can decompose them, but maybe some tasks are like a little bit harder to decompose. And it could be the case, by the way, that at some point, like in this meter benchmark, like we would reach like a threshold where basically once you can do tasks that take 1 day, you can do tasks that take 1 year by doing basically something similar to this splitting and yes. So maybe we can start with this table, or
that's what I thought as well. But, one discourse that we had was how this isn't necessarily like a good signal, perhaps, for what is like the coding proficiency of a model. In the sense that even right now, like where the models are on this like meter time horizon benchmark, I feel like there are tasks that humans can do and have done in like time frames that are much shorter than what we say the models are capable of achieving, that they still cannot achieve. But there are also things that they can do much faster that would have taken humans longer, because I feel like the amount of time that a human takes to do a task doesn't necessarily correlate with how hard the task is for the human, or how much like an AI would be good at it. And this was like some discourse that we had on the table.
So I think Meter actually showed that it does correlate, in the sense that they actually showed correlation between like the length of task and the probability of the model succeeding in it. But obviously it's not like nothing. It's not causation, and nothing is perfect. And I'm sure, in particular, if like the tasks that you ask somehow involves, if the humans for some reason is not allowed to use tools. Of course, with programming it's kind of ridiculous. But let's say you add like multiplying two numbers, then models can do it in a split second, and depending on how many digits, and if you're not allowing the humans to use tools, then it will be forever. But generally, for coding tasks, I think there is some correlation. But you're right. There's obviously like these numbers, this amount X is not a fixed number, but there is some distribution. But presumably, as X grows, the model can also do, like if right now there are tasks that take humans 5 seconds, and models still cannot do, even though like formally the models, I don't know the 80% threshold for models, what it is right now, it's 5 minutes, I'm not sure. But probably when it's an hour, maybe the models will finally do these 5-second tasks.
Yeah. Is this, the questions I guess, is this about like superhuman programming or superhuman coding? Right, because I feel like I'm not necessarily sure what is meant by coding here, because I feel like coding and programming are different things.
I don't know. I mean, I guess that they mean machine learning coding, which could involve like also some amount of machine learning research. So it's not just basically write a website, but it's more like figure out like implement some training algorithm from the literature, implement it in the most efficient way. When you have you have to distribute the coding to many GPUs, and you have to take the architecture and the cluster and all of that into account, and optimize everything from the kernels to the communication to whatever. So I think it's kind of I'm imagining this is the type of coding because this would be kind of the type of coding that you would want to. It should be kind of ML relevant coding.
I guess my problem here is one of system design because, right now, if I ask GPT to make me a website, it could do it really, really easily. But if I have the most context of what I want my website to look like, and actually getting that through is the thing that's difficult and making those choices. And so I think the thing that I feel like this benchmark fundamentally can't capture is if a task is a formal specification, it can do it in some number of hours. But for general and granted, a lot of software engineering does fit this paradigm, but a lot of it just in the sense of making design choices requires much more context that's sort of hard to give in an open-ended sense. And so, I guess the other thing is similar to Egg's point, yes, all of these, the amount of time it takes to do all these things does correlate. The constant factors, I'm guessing, vary pretty widely. And if it is a 1 hour to 5 seconds difference, I don't think it can do anywhere near what it can do in Python, for FPGA code or something like that. So I'm a little just wary of the benchmark.
Yes, so maybe the benchmark is not really exactly generally when models improve in this benchmark, they probably improve in a bunch of things, including potentially getting more better at kind of talking to you and understanding exactly what you want and then do that. But this is also maybe a point that if, for example, you were directly trying to just optimize for well-specified machine learning tasks, you might get a model that's really, really good at benchmarks, but actually will not be able to automate a bunch of the things you do, even if you are at an AI company and not a web design company. But so I guess do you guys have some suggestion for X or?
2 weeks is what we said.
2 weeks, okay. Yes.
Is this?
I don't know. Maybe it's not. Okay, so that's.
Just talk real loud.
Okay.
Okay. We honestly couldn't agree between a day and a week.
Okay, that's still some range.
Yeah.
And I guess the point is that the day is kind of what a person does and then goes. I think these are two very natural things because in some sense. You finish your work in the day and you go home and presumably you sleep and you forget some of the context and you need to renew it. So in some sense, all of us decompose things and maybe you can keep the context within a day, but then you go off to the weekend and maybe you drink. So you definitely raise some context management and you, so in some sense, these are kind of units of time that kind of makes sense and also kind of makes sense in terms of say if you have if you are have an employee, then often you would check in with them maybe when you're working very together closely, you might check with them every day, you might check with them every week, but so those would be the kind of periods of time where basically you could
have deliverables.
Yeah, have deliverables, etc.
Yeah.
So most tasks that people actually do in the real world have these kind of deliverables. Maybe some types of if you're proving a really, really complicated math theorem, it might be the case that it's more you give your grad students this super complicated math theorem and you don't hear from them for 3 months and then they come back and they prove it. But for most tasks, I guess, they are deliverables. So I think 1 day or 1 week are kind of natural things. And then maybe you could say maybe you should amplify it sometimes for the mismatch between, because it's not getting X on the benchmark might correspond to getting X divided by something on the real world, which we don't know what it is. Over there, you had yes.
Sure. I think we also had very widely differing opinions at this table, so I will give my own and then kind of pass it around. I think for me, I can give a lower and obviously with the caveats of the benchmark, accepting the benchmark.
Yes.
I think my low bounds are roughly a lower bound of like a week, again, because of like, I think if I think about how I decompose my workflow over a very long project, like roughly a week's worth of material. And then I think an upper bound, like I was like the point where I would be really forced to call it superhuman is like 30 months or something. Because that's again,
what?
I think the point at which I would be forced to really call it superhuman is like, I think 3 months or something. That's like the upper bound, because I think my projects are roughly 3 months long. If it can do that in a day, yeah, it's pretty clearly superhuman. Yeah. Yeah.
I mean, my take is whatever X is, I think we've already saturated it. Like my experience with Claude Code is we're probably at 4 to 5 hours at least. Depends on how complex the task is. I mean, some of the stuff it cooks up in like 10 minutes. It would have taken me days to code on my own. And like maybe I like have input on it like a couple of times. But I mean, we're already at the point to where hiring like a Claude Code babysitter and like having like a bunch of Claudes is like way past, you know, the output of software engineers. So whatever it is, we're already past it, I think.
I mean, so because this is interesting, because in the benchmark, I think Claude Code, I don't remember the numbers, but in the 80%, I think it's still on the order of minutes, but maybe the benchmark is somehow, you think it's somehow like the real world is easier than the benchmark?
Oh well, I mean, Claude's wall time on some of these benchmarks is minutes, but I mean, when most coding tasks are like make me a CRUD app, right, or make me a website, or make me something really basic. It's not, you know, fix this like really detailed like part of my like you know pipeline optimization, you know, distributed across like 100,000 GPUs. It's really basic stuff like, you know, make like a new endpoint on this API. And I mean, most software engineers I think are already obsolete. If you're hiring Swedes, you're wasting money.
Okay, yeah. So you're saying like basically, you're basically saying like in most companies, like not necessarily in like you don't necessarily you're not claiming that we already have the superhuman coder and we can just we don't need the best AGI company engineers, I think. Or you're claiming that
like 99% of them are probably obsolete. Maybe like there's 1% that we still sort of need, and we need some Claude Code babysitters. Like those are pretty useful people too. But Claude's really taken off though, and I mean Claude's only going to get better. So we're pretty much already whatever X was, we're pretty much already past it.
Yeah. So you basically basically, what are the people doing there right now in Anthropic? I don't know. Like,
I would assume using a lot of Claude Code, and I mean, human in the loop is important. Don't get me wrong, because you have vision, but the technical abilities, Claude's got them. Now, I think the vision and like the UX, like thinking about the UX, and you know, all these sorts of ideas from the humanities and how we have humans. I mean, that feels to me very fundamentally human, right? But the actual technical execution of getting, operable code, that's taken care of. Once you know what you want, Claude's got it taken care of from there.
Mine's actually much different. It's in the order of years. I think 1 year is the minimum, and there's some reasons for this. One is when we look at machine learning papers, like even from a few years ago, it feels like, to me, it's such a long time, but the research is actually like it built on each other so quickly.
Yes.
And that's the pace of human innovation right now. Like NeurIPS ACL is once a year. And it feels like that's the cadence. So 1 year as a measure of like having something new, a landmark, and then moving to the next landmark. I think that would be a good measure of one time step for a superhuman coder.
Yes. And I think you're thinking maybe of very kind of different tasks. So there's one task of like, let's write a website. And there is another task of let's completely rewrite our training code to do things more efficiently with our huge cluster and basically train the next generation of a model so that we are now training it to get the same performance in half the flops. And I think this is kind of like maybe you're thinking more of the second tasks, which I think you don't think Claude can do. Maybe it can. I mean,
it can definitely do them just with human in the loop. Like, okay. The harder the task, the more you need human in the loop. But still, human plus Claude will get it done way faster, way faster.
I mean, definitely, like, definitely coding agents. Like, everyone is using like these coding agents. Like, humans already now are using these coding agents, and they're definitely very, very helpful. Like, yes.
I thought we came to around 4 weeks being a pretty, if you have an AI system that can do coding tasks of that length, it's probably pretty good and probably best, mostly based on task decomposability. I think we were maybe comfortable with bringing that level down a little bit to something like 2 weeks, but there are some cases where you might see a substantial task that is longer. Anybody else?
You?
Yeah, I mean, one thing we talked about was how we weren't really satisfied with 80% accuracy, especially compared to OpenAI engineers. But like putting that aside, at least like a few of us thought like 1 week was reasonable. But yeah, we were debating between like that and a few days.
Okay.
I think similar to what people have covered, especially that table over there, we said a week based on how you can decompose it and specifically when you would periodically check in with a manager or supervisor.
I think for our table, we're a little bit uncertain on the type of task, and also I think just a quick question about the benchmark time. In the time that it takes for a human to do the work, is there an expectation on the time the AI has to do the work?
So the benchmark, I think,
or it's just faster than human.
Yeah, did not even assume that potentially, but you might expect that if at the point, say, if you achieve a certain, if the AI can do it at all, then maybe in 6 months it would do it much faster, like just because things generally improve quite fast. So even if at the moment, like maybe even if like the AI takes the same amount as a human, let's say the human takes 8 hours and the AI also takes 8 hours, but presumably maybe very quickly the AI will take 4 hours because there is really not much limitations. Or at least the manual work like should not be that. The next model should be maybe faster, cheaper than the old one. Or at least you could parallelize more also. Yes.
I think our group says about 4 months because that's typically the funding cycle. But I think personally, I would say that because AI systems may be a bit uneven, it'd be maybe more meaningful that, for example, a good engineer with the help of an AI system can reduce from 1 year to 1 week compared to a AI system being able to do everything itself in 1 day. Like a 1 day task, I mean.
Okay, so actually our first thought was that this is a really unwell-defined metric. The general sense that we thought originally was that it was going to be infinite because like specifying AGI best company is like very difficult to approximate, but
no, I mean, it's clear. It's OpenAI.
Yeah, okay, sure.
Except if you're
we approximate the best OpenAI. Okay, no, so actually on that point, if you buy into what Anthropic says, apparently like with their most recent launch of like Sonnet 4.5, they said that it was able to stay focused on a coding task for over 30 hours, which they didn't disclose what task it was or show that, which would be interesting to watch if they had a live stream of like a task for 30 hours. But if you assume that, then that already surpasses a lot of the other X times that have been suggested, which I feel like if you were to scale to some quote unquote AGI company engineer, it should be like very infinite. But then, so our like main thought process was that the reason why it would be curbed would not be because of the actual AI part, but because of the environment around it. For example, like I remember in the readings, like there was an example about like weather forecasting by AI, and that isn't bottlenecked by the AI, but by the real-time data that needs to be processed. So there's latency in the environment. And so, for example, if you're training a model, if the AI is like distilling a smaller version of itself, there needs to be time, even if it optimizes everything else that it needs to do, and then you have like 65 million models that are training, but there's still latency because those have to finish training.
Yeah, I mean, I guess the thing is like you take the human part of the system and you'd speed that up, but maybe
exactly. Yeah. I mean, unless we figure out how to train models instantly, which it might figure out. So, anyways, not well defined.
That's also like a very valid answer. Yes.
So I think like we had the same problem that some other tables had, that they don't define time for the AI to do it. Like I feel like they should at least have like a scaling, right? That like it shouldn't scale the same or something.
Yes.
But otherwise, I think like it was more of a hunch than anything else, and we said a week, and that's like, I don't know, we have a weekly meeting, so that's like a deliverable.
Yes.
But yeah.
I think we had a lot of disagreement, like a lot of the other tables. Some folks just thought that it was poorly defined, and also that the fact, like was just mentioned, the factor of acceleration mattered a lot. My personal answer was something on the order of 6 months to a year, because this is sort of the supervision time that it takes for a human to translate another novice into a fully functioning, like ramped up member of the workforce. And if you think about like the need to supervise an agent or another AI to change their objectives or bring them fully up to scale, that seems like the right measure. Else.
Yeah, we've also similarly had a problem with that 80%. It's true that weekly check-ins are useful, but would you really do only weekly check-ins with your employee if only 80% of the weeks they can actually do the work? So we were a bit cynical about that, and we kind of briefly considered just setting X to be a human lifetime, since I feel like that's the most. I mean, it's a very nitpicky answer and very silly, but that's the point where I would be definitely convinced that it's superhuman if it can do things that humans just couldn't because of time.
Yes.
Yeah, and I again kind of had a different answer. I think this benchmark is difficult because I think 80% of the work that people do is useless. Like 80% of papers barely get cited, and I would know. But so I think if we're considering this as like an equal distribution across all work, so 80% of the time you have 80% of genius papers it could write and 80% of really bad papers it could write, then I think about a year is good, because that's about the amount of time that people take to come up with a really good idea. But if we're talking about the easiest 80%, then never, because
that's a really good point. So it could be the case that you basically are doing the lowest hanging 80% of fruit, and those are just at any given time period for humans. Those are just the thing that, they still speed you up, but it's kind of like limited, and eventually that would actually be the case where basically maybe Bauman's cost disease will basically take into account, where basically the coding agents, they speed you up initially. They do kind of the 80% of the work, but then they just do the long hanging fruits, and then you're still stuck with like the main things. And and we don't know. Interestingly, like the authors of AI 2027, like they write in the appendix, there are like these two estimates. Ellie Liefland actually said like 6 months, but actually adjusted it to 10 years for these benchmarks. It said like maybe 6 months if the benchmark was really for AI engineers, and 10 years for like the actual meter benchmark. And Nikola Djokovic said 1.5 months. So they were actually very more conservative than maybe many people here. But then somehow they got like to shorter numbers. Yes?
These are very large. Look at these, like 95% confidence intervals.
Yeah, these are 80%. These are only 80% confidence intervals. Yeah, so it's like So they're very non-confident. Yes. Yeah. So I wanted to. Initially, I thought I'd show this and then ask you your estimate, but then I figured out it's actually better to first ask your estimate and then show you theirs. And it's kind of interesting because so I guess. There, like, if you were like saying a month, it would be like in 2032. Many people here said a week, which I guess is also quite a question whether a week is a work week or like an actual week. Like an actual week will be like somewhere in 2030. A work week, it's like 40 hours. Although, to be honest, like if you're trying to emulate an engineering AGI company, you need more than 40 hours.
70 hours. Yeah.
Yes. So it might be it might be somewhere like around this 2030. It's kind of interesting. I don't know how much time we have. Like how they came up. Like given that their estimates were a month, how did they come up with such short timelines? And the kind of calculation. So first of all, like from the original, they had like some updated analysis. So the original AI 2027 indeed like assumed that the superhuman encoder arrives at 2027, but then they had like some updated analysis that was less aggressive, and with various modifications, kind of depending on like what kind of assumptions. Basically, I think the assumptions were some kind of a super exponential like speed up, where as you get better, you get better, and yeah, if like we go over their assumptions, I think one of them was like the meter doubling time is 7 months, but basically they're looking at like some particular benchmark where maybe the doubling time is smaller, but I don't know if there is as much history there. And there is some probability on super exponential, and I think the way these kind of things balance out, and it puts a lot of weight on like super exponential, and there is some, like assuming that there is some internal deployment is faster, but this X is also like a certain thing which is kind of going back to like a question before. Like this meter has this very nice thing where they measure like they measure the length of time at 50% rate with a bunch of different with a bunch of different benchmarks, and each one of them each one of them you have like different like all of them grow to the extent we have data on them, but each one of them has somewhat of a different rate. So it could well be the case that basically, and this might kind of go back to the point you were making, that the model is very good at certain types of tasks, but then there will be like some fraction of tasks that are maybe where the model is much slower at getting it done. And eventually it might get done, but it might take more time. And they had another methodology, which I'll kind of skip, but there is another kind of methodology. Generally, after that, they talked about how you get from the superhuman coder to I think SAR, if I remember, it's Superhuman AI Researcher. So it's not just a coder, but does all the research. And I think so the idea was that there is a certain amount of time that it would have taken for humans to go from superhuman coder to superhuman artificial AI researcher. And because of the superhuman coder, you will do it 5 times faster. And then once you can kind of see the super exponential here. Basically, the superhuman coder speeds you up by a factor of 5. Then the superhuman AI researcher speeds you up by a factor of 25. Then you have a super intelligent AI researcher, which is like super better than so it's not just the same level as the best researcher, but much better, and then that speeds you up by a factor of 250. And then you have an artificial intelligence that speeds you up by a factor of 2000, and you can see how you basically by I don't know December 2027 or December 2027, or maybe, you take a little, give or take, maybe you update a little bit, you basically maybe arrive, or let's say by 2028 or 2029, I think you kind of can do the math, but basically, if I do the math, like then let's say by the end of 2028, we should be arriving at the progress that if we were doing by humans, it would be around the year 4028. And so this is kind of like the scales where we should have like a new religion by then or something. Like you can go backwards and see like so we should basically be having like a similar progress as we had if you compare what we have right now in the year 25 AD. So yeah, and so I guess just a kind of a sense of how you get these multipliers. Some of it I'm not completely sure. I think these things are really, really hard to estimate. But generally, I guess the idea, like this is how you get like the 5x. It's kind of basically you figured out like various factors of the ways the superhuman coder could speed up things, and then you kind of multiply them all together. So you said, okay, there is a factor 2.2 because you're able to somehow be better prioritize and put more productively use your compute on your most important experiments. And then there is a factor 1.6 because you could maybe save, like when you run an experiment, you don't have bugs, and when you run an experiment, you don't have to waste a lot of time because you have like which some of these things, by the way, I think definitely could help. Like say, if I definitely have bugs, so if and to be honest, Codex already is helping me a lot to have less bugs, and so if you run an experiment and you don't have bugs, you're quicker. If you run an experiment and you have like an AI watching the logs and figuring out like when the first time that you learned what you needed to learn and you can kill it, you save some time. So all of these factors, I don't know if all of these factors multiply together like they assume, but this is a general question. And similarly here, it was kind of partly based on this survey of 5 AI researchers, which you can also see like there is like a huge, they kind of asked this question to AI researcher, what can you do if you, how much would your company speed up if you had like each person was replaced by 30 copies of the same person, and each copy was 30 times faster. And different researchers had asked 5 different researchers had like very vastly different estimates for how much a speed like that. So I think basically, to get to the bottom line is we don't know. And I think you can imagine like the impact of AI on AI development. You can say, you can range from like not much impact, significant impact, but we kind of need it because the fruits keep getting higher. So just to sustain our current exponential rate, we'll need to use AI to speed ourselves up. You can imagine that there is like a one-time boost. We get like faster, but then we stop. Or like we shift to a new curve with like a faster exponential base, or you get like super exponential singularity. And to be honest, I really don't know. I think the only thing I can rule out, I think, is not much impact. Basically, I mean, my experience with Codex is maybe not as good as your experience with Claude Code. I mean,
that's why I use it.
Yes, maybe. I mean, I'm actually using Claude Code now, but I'm not maybe aggressive enough. Yeah, but I don't worship it.
We're besties. It works so well.
Yes.
It's the tool calls. I think they put the tools like earlier on in the training pipeline, so it knows how to use the tools. The Claude Code scaffold is like way better than any other scaffold.
Yes. We'll fix that. But yeah, I mean, it definitely has impact. Like that the one thing I say. So I think definitely AI coding tools have impact. If you're not using them, you should. Like you definitely should, and it will speed you up, and it's just like. So I think we can rule that out. And it definitely has impact not just on creating web apps or whatever you're using, but also on using it for AI. So I think that scenario we can rule out. The other 4, I don't know how to rule out. I don't know whether basically it could end up being the case that all of these companies, the AI companies, have been growing at like a crazy pace in terms of hiring. And it could be the case that basically we cannot sustain it without adding basically making the only way to sustain like the growth pace that we've already had is to make ourselves more productive by using coding tools. So we'll still hire, we'll not stop hiring, we'll not stop, but we'll just also, each person becomes more productive, and that's how we sustain the crazy rate of progress that we've already had. Another option is that sometimes there is kind of like a click and there is an unlock, and there is like a huge boost, one-time boost, but then like we continue, and then there's another thing that we just shift to a faster slope if this slope was not fast enough for you, and then there is the kind of AI 2027. When at some point we basically start to lose all way. Like the progress is so fast that we lose all way to keep up with the progress that the AIs are making, and they make 2,000 years worth of progress then in 1 year, and that's interesting. Any last questions? Yes.
I think we're like underestimating how long it takes to go from cognitive intelligence to like actual progress as humanity. Because there's lots of things where you actually need time to make like human clinical trials or to build things.
Yes.
And so to go from like just being a really good AI researcher to solving lots of real problems is probably longer than just.
That's a really good point. So yes, so so this is actually like a really good point. Like in actual making, I mean, maybe, for example, it could be the case that you do this, you have this kind of intelligence explosion, and you have these AIs prove mathematical theorems that it would have taken us 1,000 years to prove in pure math, but it actually doesn't really advance. Like, most people, like, in the day-to-day life don't really feel it when someone has proven, like, a new thing in number theory. And it could be the case that for anything that touches the real world, and even things that touch the real world, like actually running experiments to train models, but definitely anything that, like, involves medicine, like, then that would be much slower loop.
Wasn't there like airplanes still running on Windows 80 or 90?
Yes. I think that's like there is like a Windows 3.1 is running the scheduling software, I think, of one of the airlines, which is why when there was the Cloudflare thing, their software didn't actually suffer because they were still running Windows 3.1. Was one question here, maybe last one? Yes?
If you had to wager a guess as to which of the other four was most likely, which one would you say?
Ooh, I am somewhat doubtful of this last one. I kind of know. I mean, I think it's very hard to even define the exponential. So I kind of somewhere maybe between here and here, like so somewhere. So I think somewhere between we keep on the same. Two options is that we kind of keep on the same thing, or basically there is kind of a really one-time boost when you somehow get like you pick up a lot of low-hanging fruits. For example, like you're like being much more efficient because you kind of reorganize your work in a new way, and then you kind of keep going as you were before. But it's not clear to me. And, I don't really know how to predict it. Okay, one last question, please.
What is the goal, like, among these companies? Like, what do you think they, or / you,
yes.
Like, what do they want? Is it just to push it as far as it can go? Is there a vision, you think? Like, what do they want to happen?
Ooh, that's a good question. Maybe, I mean, that's an interesting question. So, I mean, the charter of OpenAI is, I guess, for AI to benefit humanity.
Yeah.
And how will that translate? And whether the way to achieve that is to just get the most AI we can at a given rate, and then figure out like how it's good. That's a good question, and it's not clear that that's the optimal approach for benefiting humanity. I think it's I think it's definitely like could be the case that it will be like that in some sense. If we manage to make sure that AI's impact is positive, then the more AI, the more positive it will be. And so, but we need to do that. And so personally, the reason I'm teaching AI safety rather than say how to train your AI as soon as possible is that I hope that we are giving a lot of focus on not just how do we get the most AI in the shortest amount of time, but also how do we make sure that the impact of AI is positive. And I think if we find scalable ways to ensure that AI's impact is positive, then it would be the case that actually the faster we proceed, or at least the more we have, then potentially the better it is. But that's the hope. We'll see how it works out. Okay, thank you.